Well, very exciting. This is very exciting. We never did these kind of things before with the AMTA, so very excited to do these little sneak peeks. We didn't want people to, forget about us over the summer, so just a little teaser here. And I don't know, as people trickle in, I think I just did this lesson yesterday with my class, right? So I was thinking, what's a good sneak peek to do right now? And I thought forces because that's what I was doing. So hopefully that helps you guys out. Um, and then I thought you might as well be able to use it right away. Yeah. Um, so I did put a I didn't put a modeling worksheet in the chat. I put an old Hewitt worksheet in the chat just to show you that you can actually use what you may be doing normally, and you may be able to use a little modeling piece, and then you can learn a lot more about it over the summer. Yeah. So just my background. So I teach in Pittsfield, Mass. It's a vocational school. We're a total, complete vocational school. Everybody in my school is required to take physics. Okay. So just in case you had a sense that, only, modeling only deals with the elite kids and no one else can understand it, or it doesn't work with anybody else. I've been doing modeling in my school for, oh God, it's been like 26 years. This is my 29th year teaching physics in Pittsfield. And I took the modeling training back in 98, and I've been doing it ever since. And it transforms teaching, or it just completely changes your classroom, and you'll just feel it when you start doing it. But you got to do it right? So that's the purpose of these workshops, is like what to do and then how to do it. And and then I just been doing it for so long that I just learn all these little, subtle pieces, right? So what I've discovered is that, all the important pieces, the salient features, if you will, of the model are the very subtle pieces. And right, that's kind of the point of these workshops. Like, yeah, you get a worksheet and yeah, you kind of see how things go, but it's the subtleties, like what happens when the kid says this, or what happens when the kid can't do that, or how do I explain this? And that's kind of what, you're kind of going for in these workshops. Yeah. And so I don't know how far we're going to get because we never did one of these before. So we're just going to crank it out here as we go. Yeah. Okay. So I'm going to share my, what I got an iPad here. So that's what I'm hoping. All right. So this is my assumption here. All right. So we're doing interactions. Yeah. Okay. All right. So what I'm hoping is that so far, if I was going to start this off, I would say, all right. So far we did right, kinematics. This would be the assumption here. All right, so we got interactions go. So kinematics first, right? So far we described motion. Yeah. So that requires completely different pre-lab procedures, if you will. So you're going to learn a way to pre-lab interactions, basically, is what we're doing here. So the key models there that you would need to have done, and different people may do different sequences, and that would be another conversation here. But so far what I have done, I would have done constant velocity, right? And then so buggy lab, that kind of thing. And then I would have done constant acceleration. Yeah. Okay. Yeah, I was just looking at. Okay. So those prelabs, so the nuts and the bolts of that is right. So you look at if I just give you a little piece of that, right? So basically what they would notice in those kind of labs is a distance and time kind of thing, right? So uh, if you took the workshops, if we had a longer version of the workshop here, then you would learn how to pre-lab those correctly so that they could kind of, they're not inventing it themselves, if you will, but you're kind of leading them, right? I guess you would call this kind of guided inquiry or whatever you want to call it. But so they're not coming up with the labs on their own. But in the end, if you show them the right thing, then they see the right thing, right? So then the gist is the questions that I generally ask them is what do you notice here? And then I would show them what I want them to see. So if I was showing them constant velocity, you show them the thing moving at constant velocity, right? The thing that you discover really fast is that uh, everybody always looks at the wrong things. Yeah. And so the first person to ever look at the right thing was Galileo, right? And he was able to do the ramp lab and then made the buggy lab a special case, right, of the ramps. And so everybody else couldn't notice the right thing, right? So noticing things is a skill, and you just watch them improve upon it as they go. So you got to teach them how to do it, because otherwise it's a complete nightmare, right? And I remember the early workshops, people had a hard time, wrapping themselves around a pre-lab because it didn't work. The kids didn't say what you were hoping that they would say, right? And there's no way to get them to say what you want them to say. They're going to say what they want. So there's ways to navigate that, right? And that's kind of what you would get in a longer workshop here. So noticing things is a skill, yeah. So distance and time get you to all those models, if you will. So you start there and then you end with a lot of different representational tools, motion maps, right? Learning how to deal with the velocity graph, solving problems verbally, right? There's a whole, you know, there's representations of the model, which is the key, right? If you're stuck just doing equations, then how many kids are you talking to, right? For me, zero. Absolutely right. I haven't solved an equation on the board in 25 years. Never show them how to do. Even my AP, I do have an AP class. I've never worked out a problem on the board, right? So as soon as you do that, then they can only just copy down what you do, and they have to have the model that you have in order to do that effectively, right? So I don't show them how to solve problems, but I show them how to use the representational tools. So the key in modeling is to distribute the model over multiple representations. And then they talk about differentiating instruction and all these words that schools and administrators like to throw out at you. But in modeling, we're doing it automatically. Yeah. So differentiating instruction just means I got multiple ways to say the same thing. And now I can reach every learner. So you just say, hey, I'm doing it, right? You say, what do you mean? You're not going to say, 25 different things to 25 different kids. If that's what they want, then, I'm finding another job, right? So I don't have to do that. I could just say, hey, where are you in the problem? Are you at the verbal part of the problem? Well, then you got to stay there, right? And if you got to draw a motion map till you get it, then you draw a motion map. So these things have to be developed and then useful for the student. But you got to feel like you can do it first, right? And I know people hated pre-labs early on, and I'm like, what's wrong with the pre-lab? And it took me years to figure out exactly how to do it correctly for everybody, right? Because teachers and students, same, everybody's the same here, right? You're learning something new. So it doesn't matter who I'm talking to. I could do, kindergarten or geriatric. It doesn't matter. I'm saying the same thing. Yeah. So anyway, there's a whole. So this would be the pre-lab. Um, that's the pre-lab for that. Yeah. Okay. So now, of course, we're doing. So this was before, if you will, right? And look, I don't know. We could talk about uh, how long this takes. And that could take. Oh, if that says before. Sorry. I have a handwriting problem, as you can tell. Yeah. There's nothing to do about it. It was my fourth grade teacher. right? Was always a teacher to blame, right? Don't forget, you're always the reason. Um, anyway, uh, so that's as before. So then now you're doing right. So now we're doing dynamics, if you will, right? And so these are descriptive models, right? It's kinematics. Just throw it in here. Descriptive models, right? So you don't ask why a buggy's doing what it does. It's just doing it, and then you go. And then same thing with a ramp or whatever you do with a ramp, a ball down a ramp or a cart down a ramp, or there's a lot of ways to do it. But you don't ask why is it doing what it does. It's just doing it. And then you go from there, right? So you have descriptive models. Um, Yeah. And now you have dynamics, right? Which is now, however you want to say it here, causal models, right? So now it's why, right? So now we're asking why, if you will, why, like what's going on here, right? So then the question is, what do you look at? Like, what do you notice, right? Um, okay. So now uh, I need a new whiteboard here. Let's see. How do I get a new whiteboard? All right, let's do it. Right. So now how do you do interactions, right? Um, okay. So so when you notice stuff, so I would normally start with an eraser, but I forgot to bring my eraser. So it's important that it's like something like an eraser for me, and you would learn more about that uh, you know, as you took the workshops in the summer. But I just got this piece of this tape roll or whatever, right? So that's the pre-lab right there, right? So it's just sitting there, right here, yeah, without giving anything away. So how do you do that, right? So that, and this is very complicated, right? So like, giving you a little heads up, the at rest condition is where we're going. This is the only problem that you can do with them. Everything else they have to be able to do. Um, but this diagram is the key diagram to understand all 6 Newton's laws, yeah? And if you're really good, I'll tell you all 6 laws, yeah? If we have time to do that. So and then this diagram shows all 6 pretty much, and this is the powerful diagram, yeah? But I'll show you I'll do both, and then if we got time, we'll do the Hewitt sheet. And the Hewitt sheet is not a modeling sheet, but it does ask the questions. I didn't draw one yet, Rich. That's why you don't see it. Yeah, I'm talking a lot. Sorry. Let's draw a diagram. Yeah. So this is the pre-lab right here. Yeah. So that. Um, so then I would say, so the pre-labs now. So in like quasi uh, quasi teacher mode here. So um, the pre-lab now is what, and then I start. Yes, I said I leave it as a blank. So I always write this on the board. Yeah, and now I say, so now I'm like, what do I look at here, right? So if I'm a kid in class, if I asked you, what do you notice? You know, you say nothing, right? And you're not wrong. There's nothing happening, right? So then the question is, what do you look at? And the answer is objects. Yeah. So you got to look at objects in the problem. So as long as you motivate that idea, that's the key. So then I'll ask you to just pop it in the chat here, and I'll pop open my chat. That way we don't have to scream and over Zoom here. So I would say, so the question would be, what objects, right? And there's several ways we can do it, but this is one way to do it. What objects affect? You could use the word interact if you want. The tape. All right. So I would ask him something like that, right? So what I would start with, very important here, tape. inside a circle, yeah? Right? So you're starting to look, and if you teach AP1 or whatever, what they're doing, all right, AP1 and all these AP classes have taken pieces of modeling and have adopted it and made it part of the curriculum, right? But what we're doing here is defining systems, and it becomes very important in solving problems, like what is the object that I'm looking at, and what is the best way to define systems, right? So you're starting this process, and it's a whole process. This is unit 4 in modeling. They won't understand the full power of the interaction diagram, which is what we're doing right now. So in teacher mode here, I'm drawing what I would call, and maybe that's what it's called, I don't think I invented the word. I think way back they called it a system schema. That was Hesteny's word, or those people who, like the geniuses who came up with it. But I never wanted to use system schema from my ninth grade, physics class or whatever. Oh, and by the way, ninth grade, 12th grade, that doesn't matter to me. I'm doing the same thing. I have ninth graders. They don't know, you know, they don't know anything, right? They're coming from 8th grade. This is what we do. All right. And they could do it. And sometimes they're better than the 12th grade. And if you teach ninth grade, sometimes you get a rough group and sometimes you get a good group, right? And the 12th graders, they're nothing special necessarily. They're older. That doesn't mean they're any smarter or better or a better worker, right? So my ninth graders could do it. They do everything the same. I don't distinguish. I can only do it one way. So whatever I'm saying to you right now, that's what I say to them, because I don't know what else to say except what I'm going to say, right? Okay, so this is an interaction diagram. I would say I would call it an ID. Then we'll do a force diagram. Okay, so then I say, so look, when I first started, I'm going to just bring this up. There's a piece of this is on the table, right? Okay. So like when I first started, I would say, okay, what objects? And then I would get all like it could be a never ending, nightmare, if you will, right? So look, high school for me, right? High school is like 80% management, right? And if you know what I mean, right? Like I can't, if you let them do what they want, it's then, just get me out of the room, right? Because that's not the way it's going to go. So I try to zero them in, and I'm not giving, like initially I thought, oh man, I'm giving this away, and I'm not supposed to tell them, what's going on. But I tell them there are 3 interactions, yeah, and then we classify them. So can I slide this? Uh, I want to slide. Slide. Can I not slide it? Why can't I slide it? Slide. Okay, yeah. So there we go. I'm getting the hang of this now. Okay, so then like up here somewhere, when they list an object, we classify, yeah? So there are only 3, right? And I'm not getting deep into like, is everything an electric interaction? And if you go there, it's over, right? Like, so don't, if you're going to worry about like, is everything electrical or whatever it is, then, maybe it is, and probably it is, but that's not what we're doing here, right? So don't go crazy like that. And it's okay to focus them, because then you don't have to entertain everything, right? So that's a little handy tip for people, all right? And look, like I said, my kid, they're no angels, all right? If you let them if you let them go crazy, they go crazy, right? So I tell them, look, there are 3, and one of them I don't care about, yeah? So we'll list, so go ahead, type in the chat. Everybody wake up, type in the chat, give me an object that's affecting the tape. Just type, if anyone's out there. I don't even know if anyone's out there, but that's okay. Yeah, so give me the 3 objects if you could. Yeah, go ahead, keep going. We got one more. You got 2. Okay. Who's the genius? Amir. Yeah, very okay, good. You got, all right, those are the 3, yeah? just to move it along here, right? Yeah, so there's no point in and yeah, so to James's point, don't let him say, it's a great point. Don't let him say gravity. It's got to be an object here, because you like, so in teacher mode, um if you let them say gravity as they're learning it, then they think there's the force of gravity is just out there acting on nothing. And we don't want that. Yeah. That just everything's done. You might as well just lecture and draw all the diagrams for them, right? So you're not wrong. We They know the word, right? But they got to list it as the Earth, and the Earth is an important piece of this, of all systems, right? The Earth exerts forces. The Earth stores energy, right? So the thing that we're trying to distinguish there, when you say gravity, there's a field, right? The gravitational field that exists without another object, but not the force. Yeah. So we're not talking fields here. We will, right? In the rest of the unit, you'll get there. And then if you really go crazy with modeling, when you do electricity, boom, you did all the groundwork for the electric field, and then you just make analogies and you go crazy with analogies. And now they're doing electric stuff the same way. So they're not new models per se. These are the core models, and then you just go crazy with them. Yeah. Right. So, okay, very good. So now they go in the circle here, right? So Earth, table, air. Okay. All right. So now I slide. All right. So slide. Okay. So let's start with the table. So I guess type in the chat, or yeah, type in the chat, because there's how many people. So we had 20 something people uh sign up, and how many we got? 7. Okay. Yeah, all right. So that's fascinating, yeah, right? That they signed up, but look, things happen, it's okay. But the fact that they signed up was good. But you guys will get a little bit of, hopefully you find it useful. I think you should. This is top of the line stuff, right? It's not my stuff, right? I'm just telling you, this works, yeah. But there's no easy. It's not easy. It's not a magic pill where, oh, they get it. But this is where the conversation starts, yeah? Without this diagram, you're just making it up. And then you have to tell them, and telling doesn't work, right? So, like, what else can I do? The answer is draw this diagram, and you keep drawing it until they get it, yeah? Okay. Uh, okay, so what's the simple way that I know that the table interacts with the tape? Can you type that in the chat? What's the simple way that we know that the table interacts with the tape? Can you do that? Yeah, even simpler than that. Even simpler than all that. I don't even care about which direction. Yes. Okay. So Amir, yes, Uh, Amir, you getting all the answers, right? So that's great. Yes. So we're gonna get to look whether or not it gets in the way, or which way it acts, right? We know it acts up, but that is not an obvious thing. So I'll show you how I do that, and you know, I, you know, it takes a long time to get these things out. Yeah. Okay. But so the first thing is I say, all right. Let me go back. So yes, so what I do here is I say the table interacts with the tape. So I draw an arrow to the tape, yeah, from the table. And I should say, look, if you've taken a modeling workshop before, people may do this diagram differently than me. And I've gotten people very upset, where they like, oh, in a different workshop, the instructor showed me something else, and I'm not doing it right. And I'm like, so that bothered me early on. I'm like, oh my goodness, like, what am I not doing right? And so then I realized, so look, this diagram doesn't have to be right or wrong. It has to be good enough. Yeah. So once you go there, this diagram could be whatever you want. As long as it identifies the interactions correctly, it doesn't matter how you draw it. Yeah. Okay. The force diagram has to be correct. So this has to lead to the correct force diagram. So you don't want to like, look, what's the way? There, if you're there, you're going to be miserable. Yeah. So these people were in probably miserable because they couldn't do it any other way but one way. And that may not be the way, right? It depends. And a lot of times I let the kids draw kind of the way they want. And in the end, they draw what you expect them to draw. And we could talk about that if we have time. But look, another handy dandy tip: motion maps and interaction diagrams have to be good enough. So they're either good or they're bad, or they're really good or really bad, right? So like if I look at someone's motion map, if I can't tell that it's like falling off a table, it's bad, right? That means their model is wrong. So they have to make it look like it's falling off a table. And now I could say, oh, it's falling off a table. And they're like, yeah, right. So if we're doing circular motion and I can't, I'm like, oh, it fell off a table. They're like, no, it's moving in a circle. I'm like, well, then that doesn't look like that, right? So that I say, you got to go back and redraw it. Like you're seeing it wrong, right? So the motion map is powerful, very powerful, but you got to let it be. If you worry about, and look, early on, I used to fight about how many dots and arrows and, it was misery. And I'm like, wow, what's happening? And then I just realized at some point, this is meaningless. Just let it be useful. And it is. It's very important. They can't do it without the motion map. And you're leaving out a key piece. So this is the same. So if you know any other rule, then just forget about it and draw whatever you want. But as long as you get the interactions the right on the force diagram correct. Yeah. Right. Okay. So there's my speech for that. Yeah. Trying to give you as much as I can in an hour and a half or whatever. Okay. So contact. Yeah. Okay. All right. So we could say that the air makes contact also, but it does something else, right? So we got to be a little careful there. So it's worth the discussion. So we'll just say that the air is touching the tape too, right? There's some air, right? See all the air there. Okay. So we could do that. All right. And then the earth, of course, doesn't make contact, right? So like so there's, I don't want to, I could drop it. It's a glass table, but it's okay, right? So if I drop that, there's the earth interaction, right? So you just drop it. So, but there's no contact, right? So I separated the air. I separated the air from the earth, if you will, right? So you don't want to confuse these things. But the earth somehow, right? The biggest mystery in physics, why does that happen, right? And now you're into relativity and all that stuff, which we kind of look. It's hard not to bring such things up. And if you read Aaron's, he actually makes a big deal about inertial mass and gravitational mass. And so he's really getting to the equivalence principle. And it's almost impossible not to talk about such things. So I can show you a little bit of what we do here. So anyway, air. And then the earth, right, of course, is a different interaction. But we know there it goes, right? It falls. So I would say, okay, that's a long range effect of the earth, right? So now we have, oh, come on. I'm probably doing all this wrong, but it's okay. So this is long range, right? And look, so here, if you want it, you could say, look, there's your word, right? I'm not saying like you can't avoid the word, right? Everyone knows the word. So look, a long range gravity, and then look, if you wanted to, you could, they know about magnets sticking to their fridge, perhaps, right? Like now, whether or not your kid, the students actually, did a lab with magnets, but a lot of them have refrigerator magnets, right? So then you could get these long range effects, right? Electricity, like they know they can get shocks. I just asked them yesterday, so they know. I say you have to touch the doorknob to get a shot. No, okay. So I got enough no's that I can move on, right? So the other thing, and we don't that those are the long. The other thing that's important with this, you got to run with the ball. So meaning once they sit, so like all I needed them to say yesterday was this diet, right? And now I run with it. So you fill in the gaps. Yeah. You can't wait for them to give you every single answer. You'll go nowhere. And that's frustrating. So, like, can I tell them? The answer is yeah. They already told you what you wanted them to say. So Amir and a couple other people threw out the objects. Now I'm running with the ball because basically I'm done. The pre-lab's done, and now I'm going to give them the rest of it here, right? So very important. And look, we're going to have to hand wave in a second anyway. So you know, just brace yourself, if you will. So I didn't give myself enough space there, but I should redraw that. That's gonna bother me. Let me give myself enough space to make an arrow. Okay, so there's my Earth circle, right? So this is the diagram right this second. Okay, that's my diagram right now. Yeah. Okay. So now you got to talk about the air. So look, the gist with the air is you bring it up and then you get it out. Yeah. If the air is in the problem, you're making it up, right? You can't do any air. We'll acknowledge it. We should test it, you know, so like if I'm doing labs with pieces of paper versus like, my classroom masses, yeah, things are different, right? So I got to make sure things fall like an eraser, not a piece of paper. But once I see that, get the air out of your problem. You never want to acknowledge air. I mean, acknowledge it, but you don't want it in the problem, right? So you might as well talk about the third interaction if you're feeling up to it, right? So type in the chat. There's two ways that the air could be a factor here. What are the two ways that air can be a factor on this? Can you type that in the chat? Or did you fall asleep? You can't fall asleep because I'm loud, right? Minimally, I'm loud. Yeah. Okay. Yeah. Yes, other geniuses now. That's a great. You guys are great. Right. So you guys know, right? So look, I bring this up right now. So air resist, right? So air, you got air friction and you got buoyancy, right? Pressure. So look, you might as well talk about it. Yeah, right. So there's the contact, the molecules touching it, right? Now look, right here, I said, look, is it a big deal? Friction, right? Air, is it windy, right? If I was outside, yeah, I'd have to maybe worry about it, right? But in the room is no resistance, right? So there's two ways here. You could just write it down here. We're gonna redraw this anyway, so it's fine. So yeah, generally they talk about an air pressure and an air resistance or something like that, whatever they say, And again, you're running with the ball, so you're gonna, you just is it windy, blah blah blah. And look, what is the percentage of? If I had to give a percentage of, do they say pressure? I say 85% to 90. I generally get pressure. And if you could lead them, whatever, like all this air is on top of the pressure. Yeah, you get it, right? They say it, is my point, right? And so they'll say resistance, they'll say pressure, sometimes right away, sometimes a little prodding, all right, but that's okay. So resistance is, now it's not windy, whatever, not, whatever you want to say, uh, you know, It's not a big, it's not like I'm sticking my hand out of a car window kind of thing, right? And then the pressure, you might as well bring it up. Um, this was actually, uh, I was at Arizona State when they would develop. I was actually Dave Hestany's grad student doing something else back in 1990, around there. I was like at the beginning of modeling. I was actually the first TA for the first, I think it was the first and modeling class that was run at Arizona State back in 1990, 91, whatever. So I was the TA for that. So I was right there. We weren't running modeling yet. We were running like the workshop physics, like Priscilla Law's kind of stuff, the real time and the workshop physics. And then Hesney's would always tell me like, oh, we got a better way to do that, and I'm like, oh, okay. And I wasn't thinking high school teacher, like, right? Who is, right? I mean, I don't know. I was like, I don't want to do that, but but he said, I was doing some other crazy thing that was a nightmare. But then he said, oh, you should always have a backup. So he's like, why don't you be the TA for this? And I'm like, oh, okay. So he's a genius, because here I am 30 years later with his backup plan. So I'll give him credit for backing me up there. That was great. So anyway, the point is, on the original FCI, there was a question about buoyancy, and they made him, he was very upset about it, but they made him, or whoever, they took it off because it was so subtle. But he was like, it should be there because we know there's an upward flow, right? So there's air under there and it's pushing it up. And if this thing was a helium balloon, right, it would make a big difference. So he was actually very upset. It's on one of those problems with the chair, students sitting in a chair, and they asked, is there an upward force of the air? That was one of the choices, coupled with the ground or whatever. And they made him change it. And I remember talking to him about, like, he's like, I have to take it out. And I forgot exactly what it was. But yeah, so yes, this is there's an upward force, right? Upward. So we can talk. I can tell you how we introduced the word force, right? And basically the way I just did it. There's no way to we'll talk about it, but I just kind of throw it out there, right? So and we can argue about that. And if you take summer workshops, we have lots of time to argue about different things, yeah. But there's an up, so they'll say that the pressure's down, right? But of course, you're deeper in the fluid at the bottom, right? So there's buoyancy. So it's pushing up, right? And I don't know if I wouldn't call it a force yet, because it's pressure. We're talking about a pressure here. So it's upward, but it's really small, right? It's not going to lift this thing off the table. It doesn't lift you off the ground, but it lets you walk around, right? Like they know the word like suction and vacuum, like they know these things, and you could just look. You're not trying to explain it. You're trying to get out of there. So you just kind of if they bring it up, great. If not, you bring it up and go and just get it off there, right? So it's small. So we're going to ignore that. We're going to ignore air. Gone, right? It's tiny, right? No chance it's lifting one of our masses off the table, right? But if I go back and do balloons, helium balloons, well, yeah, now I'm in a different model here, yeah. Yeah. So, we're interacting with this. Yeah, this is the object I start in class. Who's that? Rich. Rich, in class, it would be an eraser. Because I need something that I always use an eraser for labs because they're right. So I got the whiteboard erasers, right? They're light, but they're not too light, and I need them to yeah. Oh, you can't see me anymore? You can't see me? Ah, you can only see my board? Oh, you can now. Oh, okay. Oh, I thought I could see me. I could see you guys and me on my other screen. I always thought you could see the whiteboard and me. Oh. Okay. It may be your screen. I think you could see. I thought you could see me. All right, it's okay. Yeah. So there's a piece. There's a tape roll. There's a roll of tape on my table here. Yeah, and I use a whiteboard eraser. So I use a whiteboard eraser for this pre-lab And when I do projectiles, I use the eraser and I throw it because it looks like it kind of float, like they say it floats, all that nonsense. But yeah, so you got to check and make sure it doesn't fall like a piece of paper, right? So yeah, so we're still looking at the we're looking at the tape roll. Yeah, it's a piece of tape on my table. Yeah. Oh, okay. Oops. I'm just trying to. So the third interaction, like you might as well acknowledge it. Uh, Buoyancy, right? Due to fluids, right? So if they have trouble with the air, just put them in a pool of water, and they jet like 99, say 95% of them know, it's easy to lift someone up in the water, easier than in an air. So they know there's an upper. Like this is a quick conversation, right? And you don't want to like stay here too long because this has nothing to do with it. But you might as well acknowledge it. And I acknowledge it because Hestonese acknowledged it, and he wanted it to be important because it's something going on, right? It's the third interaction due to fluids. But if we ignore those, then it's either. So look, this is how simple it is, not easy, right? Simple and easy, different. So simple, it either touches or it's the earth, and there's no air, right? So you might as well you bring it up and get rid of it. It's that there. So simple, but it's not easy because they'll add. So look, this diagram will prevent you from adding objects and leaving them out. Because as soon as they add something in to explain what they see, it's over, right? So they have to look, if they're doing that every time, you got to back them up, right? All right, so we got to see the power here. Let's see the power. We got to draw the modified diagram. Okay, so I got to slide. All right, so now I'm going to slide here. Okay. Okay, so it's contact earth. That's it. So now the diagram looks like this. Yeah, so let me redraw it. Okay, so I got the tape. I got the earth. Yeah. And I got the table. Air is a no. Yeah. Okay. That's my diagram right this second. Okay. So now I say, all right, not very exciting. So let's make it more exciting. So the way you kick it up a notch is change focus to a different object. So then I say, how about if I ask what objects interact with the table? Could you list objects now? So a different object that would interact with the table and one that we already listed that interacts with the table. Can you do that? So the earth, yes. The tape, yes. Right? And what else? Important object to add to the diagram. Add an object. What else interacts with the table? Earth, tape, and something else is touching the table. Yeah, floor. So add in the floor. It's a good one. So add in the floor, right? And now I say, okay, yeah, there's a new. So the floor, and now you said the tape, right? And now look what you have accomplished all by yourself here. This is the key. Welcome to the third law. Yeah. So this diagram shows all six, and there's what you want. So look, any way you can get the double arrow, now you right away, forces are paired in nature, right? And now you got to lead them to see that it happens all the time, right? So now with the floor, I think you can see that the table also touches the floor. And now I got the double arrow there, right? And then you could say, hey, the earth grabs the, interacts with the floor if it wasn't connected to the rest of my house, right? though I'm at the ground level, but it still would fall, right? To the center of the earth or whatever you want to say. So then the question is, so now I have double arrows between contact interactions, powerful, right? And now, and I'm also I'm also defining a system, powerful, and now I also have identified correct forces on all the objects, powerful, and now I have to just get them to see, and I wanted to change colors here, and I probably can, but I won't waste more than I don't know how to do it, but there must be a way, but that's okay. We need to see that the tape, right? The tape affects the earth. So look, there's no magic pill for that, right? I have 30 years of doing it, and I don't have a magic pill. I do the story of I give them the apple and the moon, right? And that's really the deal, right? Because does the tape affect the earth? Well, no. But this is where you can start talking about you know, different things that go on here. So there's lots of ways to do it, but the gist is, right, so Newton sees the apple, right, and then he's looking at the moon, and the question is, are they the same thing, right? And of course they are, right? So another lab that's a good little lab to do, that's not modeling, but it gets to what Aaron's talking about. And I do this lab at some point because it's important, right? Do you guys know what this is? Someone's going to know what this is. I just did this in class. So this isn't, do you know what this is? Anyone know? Yeah. So this is a masser. Yeah. Right. So, right. So you want to, right. That's weighing stuff. Yeah. This is mass and stuff. Right. This is what you would call an inertial balance. Right. So what's the point? The point was, right, look, Einstein saw there's inertial mass and there's gravitational mass, and they're different. Yeah. And so it's kind of unavoidable that like if you get into the nitty gritty, they need a concept of this idea of mass, right? So then this gets them to see how mass is different than weight. And now, do they get it complete? It could take years, right? Years, but this is a mass. Yeah. So like, for instance, the point is you would know, right, that that's a kilogram, 200 grams. Yeah. And you could feel the difference in the mass. Yeah. And it doesn't matter if you're on the moon or in the middle of space, this thing's harder to shake. Yeah. So how do I measure that? I measure it with this. This is a shaker. Yeah. So I call it the shake and bake lab just because that's what I call it. I don't know. That's what I called it. So what basically you pop it in there, and so the time and the mass are related. Yeah. The time, just to keep it short here, right? So cryptic relationship, but that's how the universe is set up for us. Yeah. So we have celestial objects and we use them to keep track of time. But when they orbit each other, which they do, I can get mass. So time and mass, right? So you got to have a mass conversation, because then now I have an apple and now I got the moon, right? And what's the difference? Well, they would shake differently, right? You follow? So then I say, okay, look, what's the difference, right? And now you say, look, sorry, I had to mute you there. You're having a conversation. But yeah, so so the apple falls, and of course the moon is falling, but falling around, right? So you got to have that conversation. So Newton would not have been shocked at all that there are satellites in orbit, right? You can put the apple in orbit, by giving it the right speed, right? And he didn't have to do it to know. So I go on a basically just a tirade, if you will, like I'm doing right now. And I just beat him down with it that the apple and the moon are the same thing. And then the only difference would be that they would shake differently. So the moon, right? And then I say, well, okay, now they're the same. Does the moon affect the earth? And they know the moon does, right? And tides. That's good enough. So that means this thing's causing tides, and that's my best shot, right? But I'm not going to make a big deal about. I'm not pretending that I'm teaching them something there. I just want them to see that there's an arrow from the tape to the earth, and now the forces are always paired. Yeah. So now I have this diagram, right? And so yeah, gravity mass versus inertial mass is important, and Aaron's talks about it, and I didn't really understand it when I read it first 25 years ago. Like, when am I going to talk about that? But when would you have to? And that's why he brings it up. And I learned that, maybe 15 years ago, that, oh, that's what he meant, right? Like, this thing takes years. So I'm like trying to save you all these years of figuring out. I think I figured out a lot, most of it. Yeah. So that's why you take these workshops, because the people who are running them have already grappled with these things for decades. I've been grappling with for decades. So you don't have to grapple for decades. You can just ask me. Right. And so, yeah, so I'm no genius. I just didn't understand it. And I just sat there and figured out, and it took me years. Yeah. So I just did it wrong for years. And now I'm like, okay, I think I figured something out. And now we do it this way. Right. So I can save you all that trouble. And all the modeling leaders have done the same thing. So that's what you're paying for when you take the workshops, that, you can disagree or not, but 10, 15 years later, give me a call. You'll tell me that, oh yeah, I was right. Yeah. Because now you figured it out. Yeah. So, and I'm not about me. I'm not the brightest guy in the room, but I'm a hard worker. So I sat here for years just doing this and giving workshops, saying it wrong probably, and then just like, oh my god, people get upset, not understand, and I would just refine what I did. And now I think I'm in a pretty good spot. And even if I'm not, it'd be hard to tell me that I'm not. So I'm good right now. But look, I'm on to something. Okay. So this is the ID. Bang. That defines a system. Yeah. Yeah. And now I've identified forces on all the objects. Yeah. So look, there's no way to you don't have to define a force as a push or a pull. That's meaningless. Yeah. I can give you if we have time, we got to do I guess we won't get to the worksheet today, which is fine. It's in the chat though. I think, I don't know. I could pop it back in the chat. It's a great, worksheet for you to try if you have access to the Hewitt. I think it's in the chat. I don't know. Maybe it's not. I could put it back in there. But it's like you may have access to that without you needing a modeling worksheet, right? You could just do Hewitt, right? And he's got a third law worksheet, which is generally a nightmare, but not if you do it like this. Yeah. Okay. So this is the ID, right? All right. And now you say, all right, now I want to, I want the next diagram, right? So, okay. So now I say, so first I want to label these arrows, right? So the first thing you could do, I guess, I back it up. You can classify interactions based on the diagram. Yeah. And you can get everything except that the pairs are equal. Yeah. There's no magic pill for that. They just have to see it. Yeah. And that can take years, right? Like that the tape and the earth pull the same. That is the last misconception to go. and I don't know how to. This is your best shot, right? Because now you can see the pairs. You don't want to say action reaction. That's then you're done, because that gives you the sense one thing happens and then something else happens, right? You act and then someone reacts, but that's not what's happening. These things are happening together, right? There's one interaction between two objects, right? So the first thing you want to notice here, just so because it's 1 o'clock already, yeah. But we're good. You got what you got what you came for. And now I'm gonna just show you how to draw the force diagram, and then if we got time, we can look at other things here. But yeah, so two objects, right? That's very important. And now there's nothing, look, there's no fancy words, right? Fancy words are problematic. So that's why no gravity. You don't want to call it gravity. That's some fancy word, right? Like even when I talk about mass, I bring this up right on day one when we do the pendulum lab, right? Day one, you do the pendulum lab. That would be my quick recommendation. But of course, the mass could affect the timing of the pendulum, right? The period of the pendulum. It doesn't, but it's a testable quantity. So you got right away, they're bringing up weight and mass, right? And they're using these words that they don't know what they're talking about, but they're so common. So you got to acknowledge, you can't say we're not allowed to say weight because, well, yeah, what do you mean I'm not allowed to say weight? But you could tell them you don't know what you're talking about when you say weight. Oh, okay. So I'm like, hey, anyone, because they have these in their house, right? They just stand on them, but they don't have one of these in their house. And I say, anybody got one of these in your house? And they, what's it? And I say, oh yeah, what's this? All right. So then I tell them, this is mass. This is weight. And now you're really not ready. Now you don't even know what I'm talking about. So let's not talk about it, right? So yeah, you're gonna have to like hit them over the head with it, figuratively, of course, but that's the goal, right? You can't avoid these things, but you don't want them to think that they could just use words. Yeah. Okay, so two objects for a single interaction, right? And then uh the interactions are comprised. You can see it now, right? And look, people are going to say, oh, that's not the way I draw the two arrows. Draw it any way you want. You could draw multiple arrows, right? Like the table could do multiple things, right? It could cause like if it's, the hardest thing to diagram is the friction. If the tape was sliding, right? If that's sliding, like how do I diagram friction? Look, that's another layer, right? So but the point is you can do whatever you want as long as you can see, right? Like this is where I'm going with this. There are the forces on the tape. And now I know I'm right. Now I know I'm right. Yeah. If they do anything other than that, it's wrong, right? There are two arrows that hit the tape circle, and those are the forces on the tape. And now I'm guaranteed I'm correct. And so our usual assumption is they could see this diagram in their head because we just jump right to the force diagram and say draw forces, right? They're pushes and pulls. What? Okay, well, who would have this diagram in their head? Einstein, Newton, maybe not even Galileo, right? Galileo didn't have any clue about noticing objects. He noticed motion, distance, time, and he was the first one to do that. But he didn't even know why a ball would keep rolling, right? He made up a word, right? So look, this is not easy stuff. So we can't assume that they see the objects in the problem, right? That's a huge assumption. And they struggle with force diagrams. And guess what? They're still going to struggle, but now you're able to bounce them backwards, and they could say, hey, you're not ready to draw the force diagram, so don't. I always tell them, you have to stay where you are. And look, we can work the grade out so everyone's not failing the class. There are other things, right? They do labs, they do this and that. So look, you may fail the tests, yeah? They could fail the test and still pass the class, right? But that's a look, and that's a personal choice and how you want to do that. But for me, I'm just like, look, you gotta be. I'm trying to learn. We're trying to teach and learn, right? So they gotta be where they are. So even my AP students, like I got one guy. He just keeps emailing me all night, and every time the problem is a new problem. And I'm like, look, you're not ready to do it. You got to bounce back to that. They're leaving out forces on an AP exam. If you leave out a force, it's over, right? Because you got 15 minutes or so to do the problem, right? So I'm like, look, you don't see the interactions. That's why every problem's the same, the different to them, right? And they only see that they're the same when they have the full model, and he's still fighting it. Right. And he took my honors class, and he's a smart guy and he's a hard worker, but he's still fighting it. Yeah. But the nice thing here is they have a way to bounce backwards. They don't have to, it's not like, well, list your givens and there is no listing givens if you don't even know what you're talking about. That's not a thing. Yeah. So, but they can draw this, and they got to stay here. Right. Okay. So there's my speech for that. Comprised. So here's the key: comprised of a force pair. So there I bring up force. Yeah. So, you could yell and scream, oh, what's it? But there it is. Those arrows are forces. And I wouldn't define it because they're not ready for all 6 laws. I'll give them to you if we have time. But there you go. I'm not going to say what's a force, push or pull. That's meaningless. Those are forces. Yeah. And then the most subtle thing, whether you can't tell that they're equal, there's no way. But you can see that the pairs act. This is the key to the 3rd law. And you're seeing it right here. You're seeing all the laws at once in that diagram. And then the goal is to pick it apart so they can see each law separately. Right? This is a powerful diagram. Yeah. And it could take you need a full workshop to see it, right? We got to get all the way to momentum where you really define systems to see it. Yeah. But pairs act on different objects within the interaction. Yeah. That's key. Yeah. And you could see it. So that's why I like what I draw, because I could see it. And there's other ways to draw it, but that's what you want to know. The pairs are on different objects. That's the key to the 3rd law. Yeah. Now, like I said, there's no way to show, like you could use all the common ways, I didn't bring the same 2 scales, but you could pull on these scales and they're going to say the same. You could push on the force plates, the Pasco over near. There's lots of little things you could do to show them they're equal. So then that becomes a given. They're equal, but that's not enough to understand the 3rd law. That's not enough. That's like you're a yellow belt in karate, right? Like you got this piece of information, but that's not enough to understand it. So we just say that as a given. These things are equal, and now try to understand it. You're not giving anything away there, right? That's not the point. This is the point. That's the point. And now they have to see how it applies to every problem. Yeah. That's the key. Okay, so I want to show you any questions. I don't know. That's always a scary question, but I could pause right here before I do the next thing. Does anyone have a question? I don't know. You could type it in the chat if you'd rather not say it. Oh, I have a new message. No, that's great. Thank you. That's awesome. At least I know you're there, or someone's there. Yeah. Okay. Very good. So no questions. Look, it's better if there's no questions, right? You never want questions. Generally, it's can I go to the bathroom, right? I mean, I'm always like, just go to the bathroom, right? But if you get a good question once in a while, then it's icing on the cake, right? Okay. So now We got time. All right, let's do force diagram. All right. So okay, so force diagram. All right. Okay. So now so now each object gets a force diagram. I just defined the system with all what I got, 4 objects there. So the 4 objects define my system, and now I can draw a force diagram for every object. Generally, you draw the one, for the object that can possibly move, right, accelerate. You know where we're going with it. So I just, the tape can move potentially. So generally, you don't sum the forces on the floor. But if you're building a house, probably you need to worry about that, right? So you could sum look at the forces on all the objects, right? So you want to do a force diagram for the tape, right? Okay. So I've identified the 2 forces on the tape, the earth on the tape and the table on the tape. Yeah. So I know the floor does not look how nice the floor is. You see it? It doesn't touch the tape because they don't make contact. Yeah. The floor is important. You got to get the floor in there and switch. It's important to switch your focus to a different object in the system, like the table. And then immediately you said tape, and it was harder to say floor, but the tape was already in the problem, and that could be good enough. I like the floor because it doesn't touch the tape, so you can see it. The floor has no, there are no like indirect interactions. It's contact or not, or it's the earth, right? So simple, it either touches or it's the earth. Okay, so we got that. Okay, so now we want a way to write this, yeah? So look, it's very important that they do this like this, like I would say. Um, so I got so I would say in words, the force of the earth on the tape, right? So I'm getting the objects into my verbal description. That's important, right? There's a force between 2 objects, not one. That's why gravity bad, because gravity like just exists there in their mind, right? No, the earth acts on the tape. That's what we call gravity, right? So how do I write this I don't want to write those words on it all the time, right? So you say force, so force, earth on, I can use a small T for tape. So I'd write it like that. Yeah. And then I'd say the force of the table on the tape. So this is what they call uh uh agent object, but I don't know. I wouldn't call it anything. I don't think I say that. I don't know. Maybe I don't think I say it. I just say that's the way to do it. And look, in the end, you're going to call it weight and normal force, and that happens later. You can't call it that now, right? You got to call it what it is, and they got to explicitly state the objects in the problem. So then what I have to do is go back and label all the forces in the interaction diagram, right? And now you have everything, like you just solved the problem, right? You just got to know about one extra piece here, right? So I've solved this problem. So I know that this is the force of the table on the earth. I know this is the force of the earth on the table, right? And of course, look how easy it is to find pairs now, right? I could just switch the subscripts, right? And that's in books, but guess where they got it from? Someone picked it up from here, right? That as soon as you switch the subscripts, now you got the pair, right? If you called it normal force and the weight, you'll never find the pair, right? What's the pair to the normal force? I don't know. I mean, it's over if you did that, right? There's no way they find the pair to the normal force. But if I say the table on the earth, well, that's the earth on the table. Okay. And it's one thing, right? It's just one thing. So how can they not be equal, right? I mean, you know, but it's not obvious. But yeah, go ahead and label all these forces, right? Force of the floor on the table, force of the table on the floor, force of the earth on the floor, force of the floor on the earth, force of the tape on the earth. Here's the force of the earth on the tape, right? Now look at the other thing that's nice. The second subscript is a little t. If it's not, I'm looking at a different object. Yeah? So you can't get it wrong if you use this. If you don't, you'll get it wrong, right? Every time, probably. So yeah, very important that they write this. And look, they don't like doing this, yeah? So they want to just get to it, get the answer. But you got to tell them right away at the beginning, the answer is meaningless if you don't know how to do it. We don't care about the answer, right? If I tell you the answer is 6, what good is that, right? Like you got to know. So they want to just jump to it or copy somebody. I'm like, why would you like for me, I'm not assigning homework. I'm not, we're doing all this in class, right? I mean, what are they going to do if they don't get it? They're going to copy it or they'll Google it or they'll AI it. Right? I said, go ahead and AI it. Right. Guess what? I got an email from AP. He's like, I tried to AI it, but it doesn't explain it the way you do. So it was useless. So AI is useless, right? I mean, it's useless unless you know what you're doing. So we don't have to worry about AI, and they make a big deal, but I don't think it's a big deal. Like you can't hide from a whiteboard. AI can't whiteboard it for you. So I'm like, okay, like it's just another tool. Like if you can learn it from AI, great. You're like, that's great. You learned it, right? So if but I don't know. But it's a tool why would you not let them do it? I would say do it. Right? I don't care. It doesn't bother me. Okay, so that's that. So table, here's the force of the table, right? There's only 2 forces that end with the little t. And that means I got. And I know I got it because I use my rules, right? What are my rules? What are my rules? Where's my rules? Oh, over here. There's my rules. Contact, gravity, earth. That's it. Right? So really the models come down to rules. Use the rules, get it right. Make up your own rules, get it wrong. Yeah. So we have to get them the rules and then get them to see how to use it. And look, I'm not saying it's easy, but that's the goal here. What are my rules? And all my other rules were wrong. They have to grapple with, oh, everything I thought was wrong. Yeah. Everything you thought was wrong. That's not easy to swallow, right? So like, you got the 15-year-old kid, like, what do you mean? I'm wrong? Like they can't be wrong, right? They're right about everything. So this is very humbling, right? Yeah, you're wrong. So welcome to the world, yeah? Okay. So now we draw a force diagram. So now I know the forces involved. Those are the forces. Bang. Now I got 2 forces. Now I got to put them on the diagram. Yeah, not easy. Okay, this is what I've been doing. This is how I do this. And look, is there other ways? Probably. And I don't know if this is modeling per se. This is what I do. Um, so this part's you just draw your force. So So in my mind, a free body diagram is um uh, when you could have rotations where the forces don't act at the same point. But semantics, I guess doesn't matter. So for us, the object's a point. Yeah. So you got a point particle model here, right? Very important. Sometimes they're points, sometimes they're not. When we do energy, not a point, right? So like if I want to talk about a stretched spring, right, that's storing energy, can't be a point. Very important that you switch. So it's a model shift to energy, and then you got to learn how to link the 2 together. How do I link points to extended objects? Well, there are ways to link. That's a secret right now. Yeah, you got to take the workshops for that. All right, so point particle, XY grid. All right, uh, you know, a straight up and down as a default, right? We know that sometimes you want to tilt that axis, but we're not there. So you don't do, that's what they used to. All right. All right, we're down to 10 minutes. So, and AMTA needs some time at the end. So we'll just kind of get this through. So the Earth's force is generally the easiest one to do. And now you give them the one of the rules. Yeah. So they know that the Earth's force pulls down. Okay. Now you can modify that to the center of the Earth or, the center of the object. That's not important now. When you talk about the radial aspect of the gravitational force, you can talk about acts along a line between the centers. That's not, you don't want to worry about that right now. So the Earth's force is straight down, and so there's your first rule. Earth force is down. So that's always true. And as long as we're on the Earth, which we are, right? As we do these worksheets anyway, Earth is straight down, no matter what. And we'll modify that if we want to later, when we do gravitation or whatever, right? But right now, straight. So I label it force of Earth on tape. Yeah. And we'll call it, look, there's a lab, right? You do this lab and you get the weight and you call it weight, and then you move on with your life. But right now, no numbers. There would be no numbers here. So I call it that, right? Now the table's hard to get. Yeah. So, the force of the table on that, right? And people threw in different things at the beginning of the chat. It gets in the way, it blocks it, whatever, it's up, right? And of course it is up. Now, how do you get them there, right? I used to ask them which way, and I never got a good answer. Like, they didn't know, right? So then I'm like, they don't know. And why should they know? This is not obvious, right? They think it blocks it, or everything that they think. It's not that it's obvious that it points up, right? So then I do these. So then I'm like, all right, what else can we do? So then I don't want to use that one. So then I say, okay, I put the object in my hand, right? And now they know which way do I have to push, and I have to push up. Yeah. And you could see, I don't know if you can see, but the mass is pushing into my hand. You could see the deflection of my hand, right? So that's important. So my hand pushes up, right? And then I put it, and then probably the most important example is the scale, right? And this is kind of how Einstein got to relativity. He put the scale on attached to an elevator. Yeah, you like the idea of the hand. Yes, right. It's a good idea because look, guess what? Look, what happens, right? Who's that? I don't want to say your name because I'm going to say, is it name? I don't want to. I won't say it. I'm terrible at names. But yeah, you're right. So look, what happens when you switch to the hand? They say up. Oh, it's Naomi. Okay, that I can say. Yeah, but you're right. As soon as you switch to the hand, they know you got to push up. So you get like, look, you get like initially you get like, and you're like, okay, bad question. But now you're like, how about this? Oh, now you got 40 to 50% of the class saying up. That's all. Now you run with the ball. Yeah, it's up. You just got to hear up somewhere in the corner of the room, and you're good, right? Okay. So then I put on the scale, and now I'm doing general relativity, right? Because if I can accelerate it up, it gets pulled down. All the physics is right here, right? And I tell them everything's a buggy and a ramp, or more generally, everything's an elevator, right? And that's how Einstein saw it. Everything's an elevator. So he put this in the elevator, right? And the point is you can't tell what's going on if you're in the elevator in space or on the ground, right? And we don't have time to get into that. But here they can see the deflection of the scale down. So they know that the spring has to pull up. Yeah. And then the best one, and then you lead them now, and hopefully you can see this on my screen. But now I take my object and I put it on foam. Yeah. put it on foam, and now the foam gets deflected and it pushes up. And now I say, take the foam away. Oh, the table pushes up. And then look, are they all there? No, but enough of them will say up. And yeah, look, will the table deflect if there was an elephant on the table? Yeah, like at some point you'll see it bending, right? So good enough. And now you just did the one problem you can do, the at rest condition. And now now that it points up, and now you got to convince them that it's equal. And now you use the best way, I think, is to use the scale. And it's still not obvious. It's not obvious, but right, right there, right? That's balance. If I accelerate it, it's not. If I accelerate it down, it changes, but right there. But there's no magic pill for balance. So you just did the hardest problem, the at rest. But those sequence of examples work to get the force up, and then you got to do a little bit of hand waving and some magic physics there to get them to see that it's equal. But that's the diagram, right? And now those are equal, and now you have a balanced diagram, right? And everything else, then they have to draw. So you did this problem, object sitting there on the table. That's how complicated it is. Yeah. So if you can appreciate the complexity there, which if you've been teaching more than 5 minutes, there's nothing easy here, right? So the at-rest condition is the simplest of the problems. And so you just did that one in excruciating detail. And now they have to get all the other rules. So the other rules, if you want to know, the other rules are, I need a general surface rule, right? These are my rules. I need a friction rule. So you can grapple with this, as we're out of time in 10 seconds. You can grapple with, how would you diagram friction in the interaction diagram? How are you going to do it? Because if you're going to use this, you're gonna have to be comfortable with, either push your version or let them come up with a version, but they got to get friction as a separate interaction on the force diagram. So how would you do it, right? And you got to be okay with multiple things. So surfaces, right? So tilting the surface, like what's the general rule if I'm on a ramp? Friction, and then you got to model strings. Right? And strings become important because that's how I'm going to model a person in the problem, like their arm or something like that. We want to model that as a string. A massless string is the first model for people. So that's why strings are important. So you need a string rule. And that's the goal of, so if you were doing worksheet 1 of modeling, that would be the thing you would be trying to do there. And that's it. So we're out of time. So we just put a little survey in the chat. So I guess I'll just turn it over to Sue. And thanks for coming today. And hopefully we see you in the summer.
Darren,
Sue?
Darren, thank you very much for spending your Saturday morning with all of us and giving us a little glimpse into a physics mechanics modeling workshop. Please be sure to check out our website and social media for upcoming events, courses, and summer workshops. There's my email one more time if you're interested in talking about scheduling a workshop. And then finally, here is the survey, QR code and link. Thank you again, everybody, for coming. If you have any questions, I'm going to send a follow-up email with all of this information, as well as a link to the recording.
Yeah, I just put my email in there too. If anyone wanted to pick my brain, feel free to email me anytime. Dbroder@siena.edu is the best email for me.